please join me in welcoming Dr. William Gutowski.
Thank you very much for that nice introduction, and thank you all for showing up on this absolutely lovely evening. I'm almost inclined to want to be down by the beach myself. And seeing the Bruins t-shirt there reminds me to say thank you for showing up on an evening when the Bruins are trying to win a Stanley Cup. I grew up in New England, so it's special to me too. Just to let you know where I'm coming from with my title here, I am a climate scientist, as you heard, and in my view, the evidence is very strong that humans have changed the composition of the atmosphere and have changed it in a way that has caused climate change through global warming and will cause change to occur in the future. So when you see myths and realities there, it starts to give you an idea of just where I'm coming from. I should also say, because I was a grad student at MIT and I had a lot of friends who were in the joint program with Woods Hole, I know there are a lot of really sharp people down here. So, and you may know more than I do about some of the things I present tonight. So if I say anything wrong, don't hesitate to correct me. I'll appreciate it. Okay, so myths and realities. What I want to talk about tonight is what do we know about climate change? Some people that have other views, I'll say a little bit about people that are lumped together and called skeptics or deniers in some cases. And then I will also talk about these myths, some myths that are floating around, given largely by skeptics. And then try to leave you with a few words at the end about how you can discern yourself what is real or what is myth. This is obviously a very controversial topic, and there's a lot that floats around in the news and other places, and sometimes it's difficult to know what is true scientific information and what is stuff that's misleading. So this is where I plan to go tonight. So what do we know? Well, of course, one of the things we know is that global temperatures have been going up for some time, not in always in a lockstep steady fashion, but they have been going up, generally upwards over the last century and a half. This diagram here shows the temperatures from 1860 up to the present, and it's the change relative to a reference point, which I believe was the average temperature in 1960 to 1990. It goes back to about 1850, farther back in time. We don't feel that we had enough thermometers around the world making temperature measurements to really come up with a credible global average temperature. These individual dots here are the temperatures that were the global temperature for individual years, and then there's a smooth running curve here to bring out the long-term trends on that diagram also. And the yellow is some estimate of the accuracy of how well we know that global average temperature. So the main thing you see is that there have been ups and downs, but generally temperature is going upward over the last part of the 20th century. Also, just for later reference, you'll note that obviously from one year to the next you can get some rather strong changes in temperature. Again, it's not always varying smoothly with time. There's a lot of so-called interannual variability in the record. And part of that is really noise in the system in some sense, and it's part that we just can't predict. So keep that fluctuation in mind as well when I show you some later slides. Then also, 2010 here checked in as the third warmest on record by various estimates. And all the temperatures here in the current century, except for 1 year really, have been all hovering around the highest temperatures that we've had on record. So there's warming that's going on seen in the temperature record. But there's more than just the temperature record that's showing us that there is more heat in the climate system. Arctic sea ice has been decreasing. This shows the average area extent of sea ice in the month of September, which is the time of year when it reaches its minimum. It grows in the winter and then shrinks through the summer, reaches a minimum typically in September. So this is the extent of ice going back from 1979 forward. It doesn't go farther back in time because in 1979 it was when we started to have satellites flying in orbits that allowed us to view the sea ice completely, and so we could make a good measure of how far it was extending. There's been a general downward trend in that sea ice. Again, fluctuations like you see in temperature as well, fluctuations from year to year, but generally a downward trend. The sea ice is melting. Even more so, it's getting thinner. This diagram here, you can't see these numbers very clearly. It's a rather fuzzy picture, but this is the change in the thickness of the sea ice from data from the U.S. Navy. So what's shown here are numbers that are for different parts of the Arctic Ocean. Canada is over here, Siberia is over here, Europe is over here. Change in the thickness between the 1990s and records from an earlier time, 50s and up through the 70s. And the decrease is on average over the Arctic has been about 40%. In fact, most of the volume, the larger part of the volume of ice that has been lost has been through the ice getting thinner and also getting less aerial coverage, but basically getting thinner. And as I say here, the average decrease from 1980 to 2009 has been over 50%. So there's been a substantial thinning of the sea ice as well as it shrinking in its aerial coverage. Again, because of the heat that's coming into the climate system. Ice on land has also been shrinking. The key curve to look at is this blue one here, which shows the cumulative changes in ice in glaciers and ice caps and ice sheets on land from 1960 onward. And it's been generally showing a downward trend. So we're losing ice on land as well. That added energy in the climate system is not only raising temperatures, but it's also doing things like melting ice in the ocean and on the land. Now sometimes, I'm jumping ahead of myself here a little bit, but sometimes you may hear some people say that, oh, but they can find places where glaciers have actually gotten thicker or have gotten a little bit larger. Even that can happen as a consequence of warmer temperatures. Probably the most important example of that right now is the ice sheet for East Antarctica, which is the largest ice sheet on the planet. Antarctica is incredibly cold. Colder air, as many of you understand, can have less water in it. If the atmosphere starts to heat up, then the atmosphere can have more water in it. If it heats up a little bit, but not enough so it goes above freezing, then what you have in Antarctica is more snow falling out. So East Antarctica has actually been getting a little bit thicker because of global warming. So you can have glaciers in certain places that actually get thicker because there's more moisture that's being supplied to them. And then there's other aspects involving glacier dynamics, which are I don't understand very well myself, and I don't want to get into that here. But you may hear sometimes isolated examples of glaciers getting thicker. That does not mean that it's a counterexample to warming. In many cases, they're getting thicker because there's more moisture falling on those glaciers. Sea level is going up. It's going up in part because of that water on land and glaciers and ice sheets that is melting and flowing into the ocean. It's also getting thicker. It's also rising because the oceans have been warming up a bit. And we're used to thinking, many of us used to thinking of water as an incompressible fluid, but actually you warm it up a little, some, and it actually does expand a little bit. And when you have an ocean whose average depth is somewhere on the order of 4 kilometers or so, that means any little bit of expansion can lead to sea level rise. So there's various types of records that have been pieced together here to produce this record going back to the late 1800s with more direct observations in the current century. The basic trend is upward. Now, some of you with sharp eyes may have noticed that this is in units of millimeters, and the rate of rise has been on the order of about 8 inches a century or so in the last part of the 20th century. That may not seem like a lot. I'll come back to that point later on because it's not so much the sea level rise itself, it's that sea level rise in conjunction with storm surges that can start to cause problems. But nonetheless, on its own, it's also an indication that there's more heat in the climate system because water is melting from snow and ice on land and going into the oceans, and also because the ocean is expanding slightly. This a little closer to home where I live nowadays, this shows the growing season year by year from the late 1800s up to the present. Lots of fluctuations. Again, when you look at smaller and smaller areas, the fluctuations from one year to the next become larger and larger, as you would have experienced even here. It happens around the world in many places. But there's been a general upward trend in the length of the growing season. It's about 2 weeks longer now than it was earlier. And most of that is occurring because the last frost in spring is occurring later. And this is actually true over most of North America, that the growing season is getting longer. And farmers have been responding to this. Oh, sorry. Thank you for correcting me. Farmers have been planting earlier. you ask them, well, gee, is that because of climate change? And they won't admit to that, but they have been planting earlier. They want to take advantage of planting as early as they possibly can. Part of it is because of changes in variety of seeds, but part of it also is that the last frost has been occurring earlier and earlier in the year, and so they've been able to plant earlier. But again, note that there is a lot of fluctuation from one year to the next, superimposed on that long-term trend. And we know that this is because of the changes that we have made to the atmosphere, changes that we have made to the greenhouse gases in particular, carbon dioxide and methane. I'll say a little bit more about this later on. But what's shown here, this is the result of climate model simulations where they include all the known forcings. So they include the known natural forcings, which would be fluctuations in the output from the sun, volcanoes that are marked here, major volcanoes that are marked here, and then also the changes in the greenhouse gases, and also pollution that we put in the atmosphere, specifically referring to something I'll call aerosols, which are little particles that get into the atmosphere that tend to counteract a little bit some of the greenhouse gas changes. But nonetheless, when we put them all into these global climate models that are very complex, very sophisticated models, these models are able to replicate these light lines here are individual simulations. They replicate the behavior of the 20th century very well. You'll see that there is a cloud of results from these 58 simulations, and that is because of that unpredictable part of the climate system that I talked about before. When I referred to the variability of temperature from one year to the next, part of the climate system is not predictable, never will be predictable. It's sort of the noise that we'll have to accept, that we have to live with. What we see here is then also there's an average of this ensemble of simulations, which gives this smooth curve in showing the long-term trends. But this behavior here of individual simulations is very important to keep in mind because there is a certain amount of noise and fluctuation from one year to the next that we have to recognize as being unpredictable. And indeed, the real world is just one, can be viewed in essence as being like one of these simulations. So it's going to have a lot of its own fluctuations in its behavior, some of which, again, are not going to be predictable, and some of which we think we can start to understand why they occur, such as these long-term trends. And in particular, when you come to the end of the 20th century, you have this rise in temperatures, which you only get when the models include both the human factors and the natural factors in terms of what causes climate to change. If you don't have those, and I'll show you this later, you don't get that rise in temperature. This is the starting point for how where people have been able to do much more detailed work and show much more definitively that, yes, this type of warming is being caused by changes that humans have put in the climate system. Given these changes that have occurred over the 20th century, what do we have coming up for the future? When we look toward the future, one of the difficulties is that we don't know exactly how humans are going to behave. We don't know whether humans are going to adopt stringent measures controlling the emission of greenhouse gases or whether everything is just going to proceed as it has been in the past. So when we try to simulate the future, what climate scientists do is they develop various scenarios that are different plausible ways of how humans may change and how they may change the composition of the atmosphere, the greenhouse gases. And that's what these little letters up here refer to. So this is showing the temperature change from simulations through the 20th century going on into the 21st century. Going into the 21st century, you have to rely on these scenarios of how greenhouse gases might change. And they're based on different types of assumptions. This B1 here refers to a world where everybody starts to come together and try to conserve consumption of energy, but also to limit the emission of greenhouse gases into the atmosphere. And at the opposite end of that is a so-called energy-intensive scenario where basically people keep behaving as they have been in the past, and there's the world is not really working in a coherent fashion in terms of energy policy. Different nations are doing whatever they see fit to do for themselves. And in recent years, we have been basically trending along on this A2 scenario, or even a little bit above that. The economic downturn over the last couple of years took us off that a little bit, but basically we've been following that trend. So what do we see when we look towards the future? This again is the 20th century simulated by all these models. This is the 21st century. The spread here in shades is the spread among the different models and their projections of what the future may hold. We can see that irrespective of any of these scenarios, the planet is going to have this warming going on over the next 50 years. There's not much we can do about that. You might notice this little curve down here. I'll come back to that in a moment. But for plausible scenarios, there's warming that is in the system. The Earth's climate system evolves kind of like if you start to push a flywheel and it starts to move and it's got inertia to it, and you can't just stop it from moving right away. So we're on a track right now towards increased temperatures because of the added energy we've put into the climate system. And over the next 50 years, any plausible scenario suggests that we're going to have some degree of warming going on. So that suggests that adaptation is going to be necessary over the next 20, 50 years or so. After that, you see that these curves start to spread apart. And that suggests that mitigation is possible. By that I mean that we can make choices, and they're choices that we have to start making now. But we can make choices about what the future holds for our children and for our grandchildren and for their children. Choices that we make now can affect them as we look towards the future. Okay, this curve here, this one here shows very little warming. It does show some warming, but not very much. So what is that curve? Well, that's a curve where when you run these climate models, you can do all sorts of thought experiments because you have, in essence, a little laboratory on your computer. So the experiment here was, what happens if we could just somehow magically freeze the greenhouse gases at the levels they were in the year 2000? Obviously, there's no realistic way we could do that. We'd have to have a complete economic meltdown. It's not a plausible scenario, and certainly not one that I don't think we would want to wish upon anyone. But you can see that the idea of this so-called constant composition commitment run was to see what would happen if we could stop it. How much warming are we already committed to, regardless of what we might do about greenhouse gases in the future? And this actually goes up. This is in degrees Celsius. You can turn this to degrees Fahrenheit roughly by multiplying these numbers by 2. And you can see that there's still a small amount of warming that goes on through the 21st century, even if we were somehow able to just freeze the greenhouse gases at their current levels. But realistic scenarios tell us that there is warming that's going to go on, and not only that, that warming is actually somewhat greater than what we've experienced so far in the 20th century. Okay, why does this rise in sea level mean something as we look towards the future? This is the result of a study that was done for the city of New York a few years back, where they tried to take some of these scenarios of sea level rise toward the end of the 21st century and say, what is this going to do in terms of flooding at major locations around New York City? So we see Newark Airport, JFK, LaGuardia, and some of the other locations around New York City. What's plotted here are a number of different things. These white bars here is the lowest elevation at each of these sites. Not the average elevation, but the lowest elevation. And then what's plotted here in these different bars are, when it says baseline, that means that it's referring to the current frequency that flooding occurs on certain time scales. So they're referring here to a flood that may occur once every 50 years or has a 2% chance of occurring in any given year. Flood that may occur only once every 500 years or has a 0.2% chance of occurring in any given year. So very rare events, but also something that this 5 to 10 year flood is something that's more frequent. So what you see in looking at this is that flooding with sea level rise through the 21st century under this one particular scenario, situations that might have occurred once every 50 years are going to typically be occurring once every 5 to 10 years. And you see that repeatedly here. This is the current climate 50-year flood. This is the 5 to 10-year flood going off toward the end of the 21st century. And then even on a more extreme level, floods that maybe were occurring only once every 50 years or had a 2% chance of occurring in any given year would be matching what was previously the 500-year flood. So,
you talk about flood from rain?
No, this is, oh, I'm sorry, it's storm surges. So what happens is you've got the sea level rising, and then when you have storms passing by, they pile water along the shore. The storm surge. And that little bit of sea level rise is, by the end of the 21st century, is enough to make the storm surge that much worse, assuming the storms stay the same. Now, there's some thoughts that maybe some storms will get even stronger, but this is just assuming that the storms stay the same. So this is the storm surge that you get when, when a major storm passes by and it pushes water towards land. Thank you for bringing that up. And again, the point here is that even though the sea level rise may not be all that large, as you get toward the end of the 21st century, it starts to add up, and its impact is felt especially in extreme events like this, not so much in the average sea level rise. That's why I was emphasizing sea level rise earlier, even though it was a change of just a few tens of millimeters. Okay, who are the skeptics? There are two rough categories that I divide skeptics into. There are some who have provided constructive criticism to the whole notion of climate change and different aspects of what may be changing or not changing. Their work is generally founded in science. By that I mean that they publish work in the peer-reviewed literature. And then there's others that I could speculate about what their motivations are, but basically their behavior is that they will bring up old arguments and try to present them as though there's something new that nobody had thought about and was ignoring. They'll cherry pick the literature, picking out just certain isolated facts and try to make it seem like that tells us everything we need to know. And sometimes, maybe even more than just sometimes, they can be very deceptive and not tell you the whole story. The first group is actually a vital part of scientific research. In any field, we always need debate going on about whether our scientific hypotheses are true or not, and we need interaction among scientists to assess basically the truth of any scientific proposition that we may put forward. And so it's a vital part of the scientific process. We need people around to be skeptical. In fact, I would say that every scientist should always harbor at least a small amount of skepticism about global warming and just say, well, maybe there's, do we really have the full picture? Is there something we're missing? So those skeptics have been very important to our field, and they're a vital part of the whole scientific process, and you see this going on in any scientific discipline. One of the most prominent skeptics is a fellow, Dick Lindzen, who these days is at MIT. He has sometimes said some things that starts to put him in the other category in my mind, but about 20 years ago, I think he did a real good service to our community. 20 years ago, there seemed to be this all of a sudden this bandwagon effect developing based on testimony by a few people that climate change was occurring, it was real, and we knew that it was happening. And I was a little bit mystified by how suddenly everybody was just talking about global warming as though it was an accepted fact, because I'd been working on this topic. And I hadn't seen any major breakthrough. I mean, I had reasons to think that, yes, something was going on and there was a good scientific foundation for it. But at the same time, I had not seen anything that I would call a major breakthrough that would all of a sudden cause everybody everywhere to start assuming that global warming was here and now, and there was no question about it. So Dick served a useful purpose back then. He published a little essay called Some Coolness on Global Warming. And I'm not going to say that it was entirely because of him, because there's some other things that came along as well. But it was an example in my mind of where somebody put the brakes on what was really a bandwagon effect developing and caused people to go back and start to think a little bit more carefully about what it was we know and what we don't know, or what we knew at the time and didn't know at the time. And so it really helped to focus the research better in many ways. And one thing he pointed out was that water in all of its forms, whether it's as water vapor or condensed water in clouds or water in the oceans and ice, all had presented uncertainties to us, things that we didn't know very well about the climate system that needed to be studied better. And until we studied them better, perhaps we needed to be a little bit more cautious about what we were saying about what the future held. I should point out that water vapor in particular is the primary greenhouse gas in the atmosphere. We don't talk about it in the same breath as carbon dioxide or methane, because water vapor is not something that we control directly. we have not changed the composition, the amount of water in the atmosphere the same way that we have directly changed the amount of carbon dioxide or methane or nitrous oxide, the three greenhouse gases that you may hear most about. So Dick talked about this issue of water. Other people already recognize that, but I think the real value of what he did was that he pointed out that maybe we don't know as much as we think we do. And then he proceeded to publish a series of papers, and others published counter papers to his work, showing some ways that maybe water vapor might change and cause feedbacks that prevent the climate system from warming up all that much. I think the evidence is mounted against his ideas, but nonetheless, he was part of a very vital scientific process, as have been some other skeptics who have functioned within the scientific realm. And that's been very useful to our community. An example of other types of skeptics is this book published by Fred Singer and Dennis Avery a few years back called Unstoppable Global Warming. And if you can read the subtitle here, it says every 1,500 years. Now, Fred Singer used to be a skeptic who said that global warming was not occurring at all. Then he changed his mind, which is acceptable. Scientists should be allowed to change their mind if the evidence changes. And he decided that the evidence was that, yes, okay, warming is occurring, but he wanted to claim that it was some sort of a natural cycle that occurred every 1,500 years and that humans had nothing really much to do with it. Within his book, he pointed out that evidence that our warming is natural is found in more than 100 peer-reviewed papers published in professional journals with literally hundreds of co-authors that he cited in his book. So that was nice. He cited the scientific literature, and he tried to amass credible scientific evidence as given by the peer-reviewed literature. I could point out that the IPCC reports that I've been part of in various ways have relied on literally thousands of papers by thousands of authors. But science is not a democracy. Just because those reports have many more papers does not in itself make them more correct. Science is always an effort to try to discern the truth, and sometimes it's a small minority that actually comes across the truth, and it takes a while for the community to understand what the truth is. So even this is not necessarily problematical, although I do have problems with the papers he cited and some of this cherry-picking issue that I'll come back to in a moment. But even with this book here, one of the problems was, you may have noticed it had this little label attached to it that said New York Times bestseller. Well, why was it a New York Times bestseller? That usually means it's a very popular book and lots of people are buying it. Well, it got briefly on the New York Times bestseller list because they had a wealthy patron who bought up hundreds and hundreds of copies of this book. And they were all bought all at once, so it had this big blip in the sales charts, and so it got on the bestseller list because it had lots of sales. What happened with all those books? Well, they distributed them around to people in various places. I know in Iowa, they sent a couple of copies to every state legislator. I know that because that's how I got a hold of the copy I have. I was asked to take a look at it and give some comments on it, and I started reading through it, and I started putting little sticky notes whenever I had problems, and I got about 20 pages into it and had tons of sticky notes because of this issue of cherry picking, which I'm going to give you some examples of in a moment. So this was kind of gaming the system and trying to make it look like something that it really wasn't. But nonetheless, it can catch attention. Okay, so what kinds of cherry picking go on? This is not from his book, actually, because this is a more recent example. You may have heard last year that some people were talking about record Arctic sea ice. And the idea was that there had been this record growth in the Arctic sea ice, and without saying it so directly, the implication was that warming was not going on, that if the planet was warming up, you couldn't possibly have this record in the Arctic sea ice. In fact, if anything, maybe it even implied that things were cooling off. So what was this record, and what were people talking about? Well, what's plotted here is the average sea ice extent for the months of January through May, again, from 1979 to 2000. Again, it starts in 1979 because that's when satellites were able to give us an overview of the ice cover of the entire Arctic Ocean. So this shows that ice, this is the average among all those years. The ice grows through the winter, reaches its peak in late winter, and then it starts to decrease in areal extent as spring comes on and the ice starts to melt. This shaded area here gives you basically a sense of the fluctuations from one year to the next. Again, there's a part of the climate system that's always going to be unpredictable. So the shaded area in some sense represents the noise of behavior for the years 1979 to the year 2000. There are two other curves plotted here. One is this dashed curve is the way the ice coverage for the year 2000. This is plotted here because the year 2000 had the record minimum in sea ice cover when we got to the end of the summer that year. I didn't point that out explicitly in the earlier diagram, but that is the lowest that we've seen ice cover get in any given year. This curve here is 2010. So 2010 started out kind of hovering around the behavior for the year 2007. Then we got towards late winter, and all of a sudden it had this upward growth spurt, so that it ended up continuing to grow and actually almost got up to the average for 1979 to 2000, but not quite. And then it started coming down again and actually dropped back down to somewhere down here. Why did that growth spurt occur? Well, there is a late winter cold snap that occurred in the Arctic Ocean, more or less in the area north of Alaska and eastern Siberia, the western Arctic Ocean. That cold snap caused ice to form there, and so there was further growth that was occurring. That part of the Arctic Ocean had actually been devoid of ice. And in times gone by, a cold snap like that would have not produced ice growth because that area would have already been covered with ice. It would have already had sea ice present there. So there was continued growth of ice because there was an area that was now open ocean because of global warming. And it had a cold snap and the ice froze up there. And so the record was that you had the latest date that maximum ice cover was reached. Now, I heard some people going around preaching and saying, oh, this shows that things are getting colder because the ice has grown longer and longer into the season. Well, it's misleading. Either they did not understand what they were talking about, or if they did, then they're basically being misleading, because the reason why that occurred was because there's already so much open ocean where ice could freeze when you had that late winter cold snap. And again, it would not have happened in years gone by because that area would have been frozen over already anyway. The old record, not that it matters, was 2 days earlier than that in 1999. But the real issue here is that this is an example of how people will just cherry pick through evidence, present one little piece out of context, and try to give you a misleading impression, really distorting what was going on. And then this shows you what the ice cover, this is now the March ice cover, which is roughly the time of year when you have the maximum ice extent. And even in March, this is 2010 right here, the ice cover has been going down. Obviously, it covers more area. You won't remember the axis of area from the previous diagram I showed you, but obviously it's covering more area in March than in September. But even in wintertime, the average ice cover has been decreasing. This is where it was last March of this year. So it's been decreasing. Maybe there was this record in terms of the latest time that ice had frozen, but the ice cover itself has been decreasing as well as getting thinner. Another example of cherry picking. This is from a quote from Rick Santorum. He was being interviewed on Rush Limbaugh's show about a week ago, and I grabbed the quote from one website, but it's available on other websites. And I want to highlight this part that's in yellow here. But the whole quote was that the idea that man, through the production of CO2, which is a trace gas in the atmosphere, and the man-made part of that trace gas is itself a trace gas, is somehow responsible for climate change is, I think, just patently absurd when you consider all the other factors, El Nino, La Nina, sunspots, moisture in the air. Okay, so he had this statement that he made about global warming. CO2 is indeed a trace gas in the atmosphere. So he said something that was true. There was one little nugget of truth to that. The problem is he did not talk about how CO2 has an impact on how energy flows through the climate system and how changes in carbon dioxide end up preventing the Earth from cooling off, if you will, as readily as it would if we hadn't caused those increases. And that is what was misleading about his statement. He picked on one little bit of truth, and especially, where is it? Using this word trace gas, it makes it sound like it's just minuscule and of no importance. He took it out of context. He did not put in the right context, which is how carbon dioxide affects the flow of energy through our climate system. And we know that it has had a major impact on our climate system.
What's the definition of a trace gas?
Good question. Generally speaking, I think trace gases, in my experience, are things that are much less than 1% of the overall composition of the atmosphere. So water vapor kind of hovers around that level because some parts of the world, when it's colder, there's less, so it's below 1%. Sometimes it can get up to being a little above 1%. But things like carbon dioxide, methane, nitrous oxide, other gases really are sort of trace level, and they're less than 1%. This diagram here shows the impact of changes in carbon dioxide and other constituents of the atmosphere on the heating of the climate system by looking at changes between the start of the industrial era up to the year 2005. This concept of radiative forcing means that you're changing. A lot of energy flows through the Earth's climate system through light, and in particularly infrared light, as well as visible light. And by changing the composition of the climate system, you're affecting the flow of energy, and that leads to this concept called radiative forcing. I'll give you a little bit more of a context for that in a moment. But the thing I want to point out first is that when people make these estimates, very confident estimate that carbon dioxide has had this major warming effect. Anything in red here is a warming effect. Anything in blue is a cooling effect. And these up here are all basically attributable to humans. So carbon dioxide, methane, nitrous oxide, and some other gases called halocarbons have all contributed a net warming effect to the atmosphere, as well as changes we've made to ozone, basically ozone pollution in the lower atmosphere where we live. There's some changes that humans have done that have actually contributed a cooling effect as well, especially through these things called aerosols, which are little particles in the atmosphere. They can be solid or they can be little liquid particles. Basically, they come about by pollution. So soot that gets into the atmosphere, carbon soot that gets in the atmosphere is one of these types of particles. They end up having an effect on clouds, and they end up affecting how clouds reflect sunlight back to space. Their net effect, although there is some uncertainty about it, their net effect is one of causing clouds to reflect more sunlight back to space, which would be a cooling effect because the sun heats our planet. These bars right here are some indication of the uncertainty and their forcing effect. And that's the biggest uncertainty right now in terms of the effects of clouds, is what these little particles called aerosols do. If you put all the human factors together, you get this net warming effect here with a certain error bar associated with it, but still always a warming effect. And even with that error bar, it's still larger than the net effect of what we know about how the sun has changed. So this goes back to Rick Santorum's statement. Just because carbon dioxide is a trace gas in the atmosphere does not mean that its effects are minimal or trace effects. It's very important because it is a prominent greenhouse gas, and it's had this kind of change. So now I've talked about these warming effects, and I've talked about this has these units of watts per square meter, which you're probably not used to thinking of, for many of you at least. So what is 1 watt per square meter? Or this net effect here is about 1.5 watts per square meter. 1 watt per square meter is the amount of light energy that you would have passing through some area 1 square yard in size, roughly 9 feet away from a 100-watt light bulb. Or another way of thinking about it is what you would feel on your hand if you were about 1.5 feet away from that light bulb. So you might be thinking, well, geez, I can hold my hand 1.5 feet away from a 100-watt light bulb. I might feel a little bit of warming from it. What's the big deal? Well, thankfully, that's all it is. It's important because this is an average over the entire Earth. So the whole Earth is being heated by this amount, and it's been a persistent heating, something that's been gradually building up since the start of the Industrial Revolution, when we started burning fossil fuels in large amounts and putting added carbon dioxide into the atmosphere. So even though, Rick Santorum could come along and show this as well, even though this may not seem like a lot of heating, when it's persistent and it's covering the entire planet, then it starts to become a significant factor. And again, I can say thank goodness it's not stronger than that, because we would have been warming up even more rapidly with possibly damaging effects from that. Then also finally, the human contribution to CO2 in the atmosphere is not what I would say a trace contribution. This here shows the levels of carbon dioxide and methane in the atmosphere taken from ice cores, which trap little bubbles of air in them. And so we can use those little bubbles of air to see what the composition of the Earth's atmosphere was going back in time. This is going back over 600,000 years, so over 500,000 years into the past. These are the fluctuations of CO2 and of methane. And these are all, of course, natural fluctuations because they're long before humans would have been doing anything to cause significant changes in them. It says here that the atmospheric concentration of CO2 and methane is, in 2005, exceeds by far the natural range over the last 650,000 years. Concentrations in 2005 are these little upward spikes here. And in particular, the carbon dioxide in the atmosphere is 36% greater than it was in pre-industrial time. So there really is a substantial human change to carbon dioxide. It's not a trace contribution to this trace gas. It's a substantial contribution, and it's still going upwards. Okay, what are some of the myths that you hear? You'll hear people say, oh, it's just the sun. It's just fluctuations by the sun. And we certainly know that fluctuations in how the sun heats the Earth have led to major climate changes in the past. Without going into all the complicated details, we know that the ice ages and the periodicity of ice age and interglacial periods is very much related to how the sun heats the Earth. What's shown here are a couple of records of the strength of the sun hitting the Earth going back to 1860. These are reconstructed based on methods that I'm not going to claim I understand, but it's an effort to try to reconstruct what the sunlight hitting the Earth was going back over 150 years ago. There's two different methods, and so the spread between them is this white area here, which gives you some sense of uncertainty. This other curve here is the temperature record with, again, two different temperature records. So again, the spread between them is a little bit of an indication of uncertainty in what the past was. And you see that actually, if you go back over 150 years or so, that the two actually went down more or less together. And in fact, quite nicely, the temperature goes up a little bit after the solar radiation goes up, and then it goes down a little bit after the solar flux goes down, and then it goes up again. It lags behind. And that actually makes good physical sense because the Earth has lots of mass. It doesn't respond instantly to changes in sunlight. It takes a little bit of time to respond. And so, sure, we can see that probably even in the recent past couple of centuries, the changes in sunlight probably caused some changes in our climate. But now when we get into the tail end of the 20th century, the solar output was like this, pretty flat. The temperatures went up. They diverged from each other. So the sun has not caused these changes that we've seen in recent decades. And as I said earlier, people have done very careful work evaluating these changes beyond what I can get into here because it involves some very heavy-duty statistics, which I'm not going to claim I understand very well, have shown that indeed this could only have come about through the human factors causing greenhouse gases to change. Another myth. Models can't forecast weather beyond a few days, so they can't show climate decades ahead. Dick Linden, among other people, has actually made this statement. He wrote something like this in an op-ed piece in the Wall Street Journal some time ago. There's some truth to that. We know that we will never be able to forecast the day-to-day weather more than 2 weeks in advance. And obviously, if you look at the weather forecast that you get on the evening television program and stuff like that, we're not even approaching that 2-week limit. But there is, for good theoretical reasons, we know that we will never be able to go beyond 2 weeks into the future for the day-to-day weather. A lot of that comes from the work of one of my former professors, a guy named Ed Lorenz, who also is the father of chaos theory. So, and this is actually related to chaos theory, this notion that you can't forecast more than 2 weeks into the future. And then they say, so they can't show climate decades ahead. Well, that's mixing up two different things. Climate is the statistics of weather. It's the typical behavior of weather. It's not the day-to-day weather forecast. So that's a misleading statement. We can say things about what our expectation is for the statistical behavior, the average behavior of weather. In fact, humans have been doing that really for centuries. Again, referring back to where I live in Iowa, farmers in Iowa, when it comes December, January, they start thinking about what they're going to be planting come March, April, May. Well, that's a climate forecast. You can't predict what the weather's going to be on any given day in March, April, or May. But nonetheless, they're making a climate forecast. Now, you might say, well, gee, that's pretty simple because we know about the seasons. But fine. But nonetheless, it is a climate forecast. And people have been planning into the future on that kind of basis for centuries. What is perhaps going beyond that is that we now have constructed these detailed climate models that try to replicate how the real world works, and we have used those to try to determine what the statistics of weather, what the climatology, if you will be decades into the future. And in fact, they have actually done a pretty good job telling us what even the more recent changes have been. What's plotted here are these black dots are the Earth's average temperature starting in 1990 going up to the year 2005. And then this solid curve here is sort of a smoothing of that year-by-year fluctuation, again, trying to discern what the long-term trends are in the face of the noise of year-by-year variations. And then there are these shaded areas, FAR, SAR, and TAR. What are those referring to? They refer to the first, second, and third assessment reports of the IPCC. The first assessment report was based on climate models. It came out in 1990, and it was based on climate models that were producing their climate projections in the late 1980s. So they were basically predicting this whole 15-year period. The second assessment report came out in 1995, and it was based on models that were running in the early 90s. So they were basically predicting this part of the period. And the third assessment report came out in 2001. So the models were, in some sense, only predicting just the tail end of this. The colored bands here, again, are the spread among all the different models, accounting for some of the noise, if you will, in climate simulation, and also some of the uncertainty because our models are not perfect and they have error in them. But what you can see is that they're basically collectively all tracking along the same way the real world has tracked along over that same time period. Even these very highly simplified earlier models have done a very credible job of telling us what the climate change was going to be over the last part of the 20th century going into the 21st century. So, and by saying credible job, that means in part that not only are there colored bands encompassing this solid curve, but they're not a factor of 10 higher, saying that the changes would have been on the order of 7, 8, 9, 10 degrees, or a factor of 10 smaller, saying that the changes would have been only a few hundredths of a degree. They're really tracking what's gone on pretty well. So this statement is really not true. Climate has changed without humans. It's all natural cycles. This is the counterpart to that figure I showed you before that had all the forcings, human and natural. This has the natural forcings, multiple simulations, giving you all these light blue curves here. And also the black curve is the observed temperature record. You can see that they track along fairly well, except when you get, again, toward the end of the 20th century, and then they spread apart. The natural changes, the natural forcings of climate cannot explain what has been happening in recent decades. So it's not just natural behavior. Then in addition, this is something going farther back in time. This is going back to about the year 700, year 700 up to the present. This light solid curve here is that temperature record I showed you before. The shaded stuff is the result of people trying to reconstruct what the temperature was for the northern hemisphere using all sorts of so-called proxy records, different types of indicators, tree rings and other things to give an indication of what temperature was. Where the colors are darkest, those are the places where these various reconstructions have had the most agreement. And so that's where we have the most confidence in our reproductions in the past. And we see that there have been fluctuations going on through the past, but this is really pretty much unprecedented, this warming that has occurred in recent decades. Perhaps a little bit of a hint that someone had a reconstruction that suggested something comparably warm for a brief period, but that's not been what the bulk of the reconstructions have shown. So there's no natural cycle that this is really fitting into on the timescales that we're looking at. As a little aside also, this type of diagram, because of its shape, like this, with this sharp upward trend, has been sometimes referred to as the hockey stick diagram, which comes to my mind tonight especially. But you might sometimes hear this controversy of the hockey stick, because there's some skeptics who didn't like this kind of reconstruction. They've tried very hard to knock it down, and have not succeeded, in my opinion. A couple of last ones. Cosmic rays are changing. Well, this is one actually that Fred Singer hopped on. There's some people who have pointed out that cosmic rays, which are little particles, energetic particles coming from outer space, can act as little particles that help clouds form. Clouds form when they have little particles that water can condense on. A problem with that is that there's so many other things out there that water can condense on. There's salt from the oceans. There's dust from the land. There's also the pollutants that humans have created. These cosmic rays would seem to be just a small addition to that. But more to the point, the UK Met Office pointed out that there's been no evidence that the flux of cosmic rays, that is the amount of cosmic rays coming into the Earth, has changed in any substantial way over the last 30 years. And they point out decreasing because the notion here is that if you have fewer of these particles coming into the atmosphere, you get fewer cloud particles forming, less cloud cover, so the sun would heat the Earth up more strongly. But there's no evidence supporting that. Fred Singer, again, really was promoting this, but there's no substantial evidence in support of it. Then finally, in the 1970s, the scientists said an ice age was coming. Now they flip-flopped. The notion for that is this is from those same ice cores. These gray shaded areas are interglacial periods. This is an indication of global temperature from oxygen isotopes. And so we had these interglacial periods where it was relatively warm, dropping off to an ice age, warming up again, ice age, warming up. And so you had these interglacial periods of varying lengths. This is the current one we're in right now. And so when scientists were looking at the temperature record in the middle of the part of the 20th century, they saw that temperatures had gradually gone down a bit from the 1940s to the 1970s. And so there was just some very speculative musing, if you will, that perhaps we were starting this long downward slide towards another ice age, recognizing that it would take hundreds and thousands of years to occur. And there was maybe one or two papers published in the peer-reviewed literature on it. But it was not like there was this big groundswell of scientists saying, oh yes, we got an ice age we got to start worrying about. It was very speculative. So again, this is being taken out of context, trying to exaggerate what was very speculative thinking and recognized as being really very incomplete thinking even at the time, that maybe we were perhaps possibly, putting all the qualifiers I can put together, heading towards an ice age. But we're not. Okay, so what can you do? When you read the newspaper, when you see the news, if you go on the internet, start looking at all the blogs and stuff like that, you come across all sorts of discussion going on. It's always hard to figure out what it is truth and what is not. Some things that you can do is don't rely on one source of information. And by that I would include myself. Just because I'm saying it, don't just come to me and ask me for the truth on climate change. It really involves looking at multiple sources. Watch for false balance. Reporters have a very difficult job reporting on science because they have to cover so many different topics. One way to try to at least give a semblance of being objective is to think, well, if there's some issue here, then maybe there's a counter view to that issue. So they'll try to balance off one side with another. And I know that there are some skeptics who are climate change skeptics because they love attention. And they like to take a counter argument basically so they can get attention for themselves. So false balance can be misleading. This is a quote that's been attributed to Mark Twain, but many others. Watch for carefully selected data, and as Mark Twain and others said, watch out for lies, bleep, bleep lies, and statistics. The notion here being that people can misuse statistics in various ways, and I gave you a couple of small examples of that this evening. But perhaps the most useful piece of guidance I can give you is to be wary of information sources that attack the credibility of their opponents, engage in really childish behavior of name-calling, and provide little evidence from the peer-reviewed literature. They just say, oh, I heard that somebody said this. But especially these first two things, and this is where I especially fault Fred Singer's book, was throughout his whole book, he just starts trying to attack the reputation. He engages in very childish behavior like this. Anytime you come across that by anybody, and I would say probably in any scientific area, but and I would say even if you are seeing something written by somebody who is a proponent of human-caused global warming and they do this, start to tune them out because you're not sure what their credibility is. There are various sources you can get information from. I've got a few listed here, which I'm not expecting you to remember anything, but I also have my email address here. I certainly welcome you to come up here afterwards and get that, write it down, and you can contact me if you have further questions. Again, keeping in mind the first point I made on the previous slide, don't rely on just any one source of information, but I'd certainly be happy to talk with you, whether you are skeptical or not skeptical or whatever. With that, I will say thank you for your time. Thank you for coming out on this lovely evening, and I'd be happy to answer any questions that you may have.